Okay, so the quizzes, the overall quiz scores were, kind of low. I mean, it's the first quiz, so hopefully getting the first one done will give you a sense of what kind of questions I'm going to ask, a little better sense. But let's go through the answers to this one. So, quiz one. The first question was, what one thing needs to be chosen before time can be expressed as a number? You need to choose instant corresponding to time equals 0. So if, anything like this, I would have given you credit for, but you can't put a number to time until you choose what essentially is turning when you're going to turn the stopwatch on, okay? Once you turn the stopwatch on, every instant is associated with a time, with a number. The second one, am I reading the right quiz? This is, right? Because I have a different one for the night class. Okay. What two things need to be chosen before position can be expressed as a number? So those are, you have to choose a location corresponding to 0 position, and you have to choose a positive direction. So those are 1 and 2 gives all the things that you need to choose so that you can represent instants in time, not by describing them, but just by numbers. Number 3, in 1D motion, what indicates the direction of a directional quantity? The sign, so plus or minus. Fourth is, what is a particle? In physics, a particle isn't an actual description. Like when you describe a particle, you're not talking about what it physically looks like. You're saying you're treating some object as if it has no length dimensions and therefore no orientation. It does have mass though, so I don't know, I'll list a whole bunch of these things we talked about, and for the most part, if you gave me any of these, like you were sort of on the right page of your notes or whatever, I gave you credit for this. So treated as having no length, and because of that, no orientation. And it can have mass, does have mass. And then the last one was a conversion problem. So to convert 1,050 miles per hour into meters per second, 1 mile is equal to 1609.344 meters. And 1 hour is equal to 3,600 seconds. And you get something like 469.392. I actually didn't, I gave full credit for that, even though it says scientific notation. But 4.69 times 10 to the 2 meters per second. Any questions about the quiz? And the next quiz is Thursday, right? So what you need to do to get ready for the quiz is you need to read back over your notes, remind yourself what it says in the notes, remind yourself what the major things I was trying to emphasize in the notes are. And then you should also skim back over your homework problems and make sure you remember how to do them, because there's always, well, most of the time there's going to be some homework problem on there that's already been assigned. Okay, I won't assign anything, I won't put anything on the quiz that I assigned today, but the things before that will be on there. Okay, and you can focus, yes. Yeah, that's what I was just going to say. You can focus on since the last quiz. Okay. But I haven't started yet, but around now I'm going to start when I give those assignments. It's not just going to be reading today's, rereading today's notes. It'll also say, read over the notes from whatever the date of the first day of class or something. And so I'm going to be assigning things that'll make you go back and rework stuff. Some of the old problems I'll assign again, just to try to stick it in your head a little better. And so when you take a quiz, that won't apply on Thursday, but when you take a quiz, and in the past 2 weeks, I've assigned some of these old problems and assigned reading some of this old stuff, that'll still be eligible for the quizzes, whatever I've assigned in the last couple weeks. Okay. So we were talking about free fall, and we talked a bunch about what are the physical things that make free fall a good approximation of an actual occurrence. The first thing is, this is non-negotiable. The object can't be touching anything, okay? So nothing sitting on the table is in free fall because it's touching the table. And then also, the air resistance effect on the motion has to be negligible. And that's what we talked about in lab, and we talked about that a bunch last time. And if those conditions are met, then we say that the object's in free fall or projectile motion or ballistic motion. Those all mean the same thing. And that means that acceleration is 9.81 meters per second squared directed down. And I talked about this once before. So how could it be that, an object in projectile motion can be moving up, it can be coming down, it can be moving sideways? How can the acceleration always be down? And the answer is that the direction it's moving doesn't tell you the acceleration. The direction it's moving tells you the velocity. Okay, so if you choose your positive direction up, well, before we think about signs. So if an object's on the way up, the direction of the velocity is up. Okay, but if the direction of the velocity is up, and on the way up, is it speeding up or slowing down due to gravity? Slowing down. So if the velocity is up and it's slowing down, what direction does the acceleration have to be? Down. And if it's on the way down, what direction is the velocity? Yeah, it depends on what you choose as your positive direction, but it's down. And is it speeding up or slowing down? Speeding up. And so if velocity is this way and it's speeding up, what direction is acceleration? Down. And so no matter what the thing is doing, if it's in free fall, projectile motion, the acceleration is down at 9.81 meters per second squared. And that's a really easy thing to get wrong. I think it's because acceleration is so hard to visualize. It's hard to have an intuitive sense of what acceleration is, it's easy to get it mixed up with velocity. So I think the best thing to do is think of velocity intuitively. The direction of the velocity is the direction the thing's going. And then think of acceleration only in terms of those mathematical things we talked about. Is it speeding up, slowing down? Later, when we get to 2 dimensions, it'll also have to do with whether the object's turning or not. But that's the way to think of acceleration, how the velocity is changing. Okay, so let's just do a few examples of free fall problems. So let's say a ball is thrown straight up into the air. At 10 meters per second. From a starting height of 3 meters. The first question is, how high is the ball at the highest point? So if you throw something straight up into the air, it goes up for a while, slowing down. Finally, it gets to a highest point before it starts coming back down. So what's the ball's maximum height? And then the second question is, what's the ball's velocity the instant before it hits the ground? Free fall problems are constant acceleration problems. The one thing that's different between free fall problems and other constant acceleration problems is we always know the acceleration. So we're going to start out the same way. We're going to choose these 4 things. Choose an instant corresponding to time equals 0. Choose an instant corresponding to time final. Then a positive direction, a 0 position in a positive direction. And the 2 that we can't get wrong, that if we get wrong, we'll get the problem wrong, are time equals 0 and time final. Those have to correspond to instants where we know stuff and where we want to find stuff. Okay, so what are the 2 instants where, so if there's an instant where we're looking for information, that for sure has to be one of those 2. And then second, we're looking for instance where we're given information. So what's going to be our time equals 0? The first instant where we either know stuff or want stuff. Yeah, the instant it's released. At that instant, we know something about where it is. It's 3 meters off the ground. We know something about its velocity because we know the direction and the speed. And then what do we want to choose for time final? We're looking for where it reaches the highest point, and so that has to be our time final. If we choose the instant where it hits the ground to be time final, we don't have any way of calculating that thing that happens somewhere in between those 2 instants. Okay, so time final is when it reaches the highest point. Okay, so here's an important question though, because eventually we're going to have to turn all these things into values. How are we going to specify when it's at the highest point? What is it about an object when it's gone up for a while and it's reached the highest point and then it changes directions and starts coming down. What do we know at that instant? That's right, the velocity is 0 at that instant because when it's first released, it has a big velocity and then it gets smaller and smaller until it reaches the highest point. At that instant, it has 0 velocity. And from every point after that, it has a downward velocity. Okay, so it's right at that point where it switches signs. That means it has to have 0 velocity. So this should say reaches highest point. So anytime in a constant acceleration problem, the sign is switching, the sign of the object is switching from one direction to the other one. It's going from a positive sign to a negative sign or a negative to a positive. You know that velocity has to be equal 0 at that instant that it switches directions. Okay, now these are arbitrary. We can do this problem no matter what we choose for these. But for position equals 0, I tend to choose the ground. Excuse me. Thanks. I tend to choose the ground beneath where the object is at time equals 0. So let's use that. And then for the positive direction on free fall problems, I'd recommend that you just always choose the positive direction up. And notice that if you choose the positive direction up, since the acceleration is always 9.81 down, that makes our acceleration always negative 9.81 meters per second squared. So I like to just always do that the same way. I think it minimizes the number of mistakes you make when you're thinking about signs and stuff. All right, and now we're going to figure out what we know and what we want. Let's see. So let's just go through the list of all of those 6 variables. Do we know time final? Like, do we know how many seconds it is from? No, we don't know that. If we can get by without knowing that, that's fine though, right? We're not asked for it, so I'm not going to put that anywhere. Do we know the position when time is equal to 0? Yeah, at time equals 0, we know the ball is 3 feet above the ground. The ground is 0, up is positive, so is that initial position positive 3 or negative 3? Positive, yep. I'm going to put the signs on these just to sort of emphasize that we have to choose those based on our positive direction and where our 0 is. Do we know the final position? What we're trying to find is the position when time is equal to time final. So I'm going to put that over here. We're looking for PF. Do we know the velocity at time equals 0? Okay, yeah, so we know that the speed at time equals 0 is 10 meters per second. And do we know the direction it's going? It's up, and is up positive or negative? Positive, so the initial velocity is positive 10 meters per second. Do we know the final velocity? The velocity when time is TF? That's 0, yep. That's how we specify that it's at the highest point. And last, do we know the acceleration? Yes, we always know that in free fall problems. So negative 9.81 meters per second squared. Is there an equation that works with these? Yeah, the third one that I gave you, 2A times the quantity P final minus P initial is equal to V final squared minus V initial squared. So we have 2 times the quantity negative 9.81 meters per second squared times the quantity P final minus 3 meters is equal to 0 squared minus positive 10 meters per second squared. And so that's negative 19.62 meters per second squared times the quantity PF minus 3 meters is equal to negative, you have to square the 10, and you have to square the meters and the seconds, so negative 100 meters squared per second squared. And now I'll distribute that first set of parentheses through that second set. So we have negative 19.62 meters per second squared times PF, and then plus negative 19.62 meters per second squared times negative 3 meters. So negative 19.62 meters per second squared PF, and then multiplying this first set of parentheses times that second term, you have 2 negatives, so you get a positive. And so you get 3 times 19.62, that's 58.86. And then the units, we have meters times meters divided by seconds squared, so meters squared per second squared. And all that's equal to negative 100 meters squared per second squared. And now we can subtract 58.86 from both sides. We get negative 19.62 meters per second squared times PF is equal to negative 158.86 meters squared per second squared. And then the last thing is dividing both sides by stuff in the parentheses. So PF is equal to 158.86 and we have meters times meters in the numerator, seconds times seconds in the denominator, and then dividing by the negative 19.62. So in the denominator we have negative 19.62. Thanks. So in the denominator, negative 19.62 meters, seconds times seconds in the top. And now make the cancellations. One of the meters cancels, all of the seconds cancel. And you get positive 8.10 meters. So the ball is launched or thrown or whatever from 3 meters in the air, and before it stops, it makes it up to 8.1 meters, and then it starts falling back down. Any questions about the first part? Yes. Yeah, we chose our positive direction to be up, and I would say always do that. And the acceleration is always down at 9.81 meters per second squared. So that means that the acceleration is negative 9.81. And if you always choose the positive direction up, that's always what the acceleration is going to be, negative 9.81. Okay, so now we want to figure out what the velocity is right before it hits the ground. So let's think about these choices. Past, when we've done different parts of a problem, we've always been able to use those same 4 preliminary choices. We're going to be able to use 3 of those the same, but one is going to have to change. So time equals 0, we can still let that be the instant it's launched because we still have a bunch of information there. But now if we choose time final to be when the object gets to its highest point, we don't have any way to calculate what happens later when it hits the ground. So now we have to change our time final to be the instant right before it hits the ground. All right, so how are we going to specify when it, right before the instant, right before it hits the ground? What do we know about the ground? That's right. We chose the ground to be our 0 position, and so that's when the position is equal to 0. And our p equals 0 and our positive direction, we're keeping both of those the same as in part A. Okay, so think about what we know and what we want. So do we know time final? Do we know how long it takes from when the ball is launched to when it hits the ground? No. Do we care? No, so leave it off. Do we know the position at time equals 0? Yep, that's still positive 3. Do we know the position at time final? That's 0. Yep, that's how we're letting this equation know that we want the velocity when it hits the ground. Is we're going to specify that our final position is 0. Do we know the velocity at time equals 0? Time equals 0 is when it's launched. So yeah, we know that VI is equal to positive 10 meters per second. And do we know the final velocity? No, that's what we want. And then acceleration is negative 9.81 meters per second squared. Is there an equation that will work with these? There's no T final in this, so if there's any one that's going to work, it has to be that third one. That's the only one without time final in it. So let's use 2A times the quantity PF minus PI is equal to VF squared minus VI squared. And so 2 times negative 9.81, I'm going to just lump that together here as negative 19.62 meters per second squared. And that's multiplied by the quantity 0 minus 3 meters. And then that's equal to v final, what we're trying to find, minus 10 meters per second squared. And so we get positive 58.86. Am I doing that right, or is that 58.88? Yep. Yeah, because we still, our time equals 0 is still the instant it's launched. And so that means that our velocity at time equals 0 is the velocity when it's launched. We could have also done this problem by saying our time equals 0 was when it was at the highest point, and then use the information we got in part A to do this. But I just kept it the same. It works either way. Can someone multiply that? 0.86? Okay, thanks. So 58.86 meters squared per second squared is equal to VF squared minus 100 meters squared per second squared. Add that to both sides, and I'm going to switch the sides of things. So V final squared is equal to positive 158.86 meters squared per second squared. So how do I find V final now? Square root, yep. So VF is equal to the square root of this, which is 12.6 something. And you also have to take the square root of the units. Square root of meters squared per second squared is meters per second, so the units come out. Right. This is not. I skipped something important. Yeah. When you take the square root, remember, the answer is plus or minus. So now we need a way to decide which one is the answer we want. This is giving us two answers, and that's not good for us. We want a single answer. We don't want, we don't want a choice of possible velocities. We want to know what the velocity is. So which one of those two makes sense for the velocity right before it hits the ground? Positive or negative? It's negative is the one that makes sense. And the reason that makes sense is because right before it hits the ground, the ball is moving down. And if it's moving down and our positive direction is up, that means negative velocity. Any questions about that? Yeah. So first of all, after we take the square root, we have two possible answers. So we still have some narrowing down to do. We have to decide on one of those. And so a positive velocity means the thing is moving up. A negative velocity means the thing is moving down, because that's what the way we chose our positive and negative. So right before it hits the ground, we have to ask ourselves, is the ball object going to be moving up, or is it going to be moving down? It's down, so the answer is negative. Yes. Yep. You get the same answer. The velocity would be 0. The initial position would be 8.10, and you'd get the same thing. Yep. Okay, so let's think about a position versus time graph of this motion. Yes? Yep. And that velocity would end up being positive. Yep. That's right. But I would recommend, I mean, you can do what you want. I won't mark, like if you choose a positive direction down, you like doing it that way, that's fine with me. But I would recommend that you always choose your positive direction up. It just makes the process more consistent. All right, so let's think about what this motion looks like on a position versus time graph. Well, we know a couple of points. We know that when time is equal to 0, the height is 3 meters. And we know that the highest point is 8.10 meters. And then, we eventually know it comes down there. Position versus time graphs for free fall motion are always going to be parabolas. And so this parabola looks something like, move this down. Okay. So what does that negative 12.6 velocity look like on this graph? Well, this is the instant when it hits the ground. And do you remember what instantaneous velocity represents on a position versus time graph? It represents a slope at that instant. Slope of a tangent line. So if I draw a tangent line to this graph here, then the slope of that line is negative 12.6. And what about that other answer? So this is the only one that makes physical sense. But there must be, but the answer positive 12.6 makes mathematical sense. We know that there were 2 solutions to this. So what do you think that other, how does that other 12.6 show up on this graph? That's pretty close. It's actually, if you extended this parabola down into the negative times that we don't deal with and drew a tangent at that instant, because remember, we specified that the position had to be equal to 0 at our time final. So these are the 2 places where position would be equal to 0. And that positive 12.6 is the slope that would happen over here at negative some time. It's not a physical solution, but it's a mathematical solution. So this one has a slope of positive 12.6. But none of this stuff happens. Also, none of this stuff happens because the ball doesn't go through the ground. It hits the ground, and then it's not constant acceleration anymore. Yep, I think that's pretty great. Okay, so let's do another one. Anybody have any questions before I go on to another problem? Yes. Because air is a bunch of little things, and think about a little thing. Think about like a one of those inflated clowns with the weight at the bottom, okay? And think about if you're on your bicycle, would you rather hit that going really slowly or really fast? It hurts more if you hit things going really fast. And it hurts more because they're applying bigger forces to you. And that's the same thing that happens with air particles. The faster you're going, the harder they hit you. Okay, so here's the next example. So let's say you are at the top of this bridge. Okay, there's the railing of the bridge. That's the railing of the bridge. Here's the water. And you're standing over it. That's you. And you're wondering how high this bridge is. You know, is it safe to dive? Something like that. Okay, so you don't have a tape measure that long, but you do have a metal ball, something that you can drop and you know, from a reasonable height, and you don't think air resistance is going to affect its motion too much. And you have a stopwatch. Okay? So how are you going to figure out the height of this bridge using this metal sphere and a stopwatch? You're going to drop this object into the water and time how long it takes to hit the water. And then you're going to do this calculation that's going to let you calculate how high the bridge is. But you should be super, super careful if you ever do this about boats. Okay? Because okay, so this object is dropped from the bridge. And it takes 1.50 seconds to hit the water. How high is the bridge? First thing we have to do is choose these four things. Time equals 0 is probably, it's going to be when it's released. Time final is going to be when it hits the water. Position equals 0. I'm going to make that choice the same way I did in the last one. I'm going to make it like the water right below where it's dropped. Below the release point. And since it's a free fall problem, I'm going to choose the positive direction up. And now we have to think about what we know and what we want. Do we know time final? Do we know the time, the number of seconds between time equals 0 and time final? Yep, in this one we do. Time final is 1.5 seconds. Do we know the position when time is equal to 0? No. Do we want it? Yeah, that's what we're trying to find. We're trying to figure out, you know, where that rock is at the instant it's dropped. So P initial is what we're trying to solve for. Do we know the position final when time is time final? We do know that because we're turning off the stopwatch when the rock or whatever hits the water, and that's time final. So position final is whatever the water is, and we chose that as our 0. Do we know the velocity when time is equal to 0? Okay, so this is something that is going to be really useful in a lot of problems. If you have any problem that says something is dropped, not launched or thrown or projected in any way, if it just says an object is dropped, at that instant, the object's velocity is whatever the velocity is of the thing it's dropped from. Okay, so if it's dropped from a bridge, it has the velocity of the bridge, which hopefully is 0. That's what you look for in bridges, If it's dropped from the window of a car, at the instant it's dropped, it has the velocity of the car. If it's dropped in an elevator, at the instant it's dropped, it has the velocity of the elevator. Okay, so velocity initial is 0. And I'll write here, since it's dropped, so it has the velocity of the bridge. Just at the instant it's dropped, and then everything changes. Like if you take a tissue paper and you're driving down the highway and you drop a tissue paper out the window of the car, it won't keep, at that instant you release it, it'll have the velocity that the car has, but it'll change really fast. The wind's gonna slow it down really fast, and so it's gonna disappear behind you. It's gonna look like, but at the instant you drop it, it really will have a velocity of 60 miles per hour or whatever. We know the final velocity, the velocity at time final. That's when it hits the water. Yeah, do we know the velocity there? This can be sort of a tricky thing for people. So I think that, remember that our time final, when I say that's the instant it hits the water, what it really is always the instant right before it hits the water. As soon as it hits the water, it's not in free fall anymore, and our equations don't apply. Okay, so this is only good up until just before it hits the water. And just before it hits the water, we don't know what the velocity is. So V final is 0. No, that's what I was just saying. We don't know V final. V final is not 0. And then the acceleration, we know it's negative 9.81 meters per second squared. Is there an equation that works with these? I think probably the second equation will work. That says P final is equal to P initial plus V initial times time final plus 1/2 A times time final squared. So 0 is equal to P initial plus 0 times time final is 0 plus 1/2 times negative 9.81 meters per second squared times 1.5 seconds squared. And so I'll move this term over to the left side of the equation. I'll write it like this. So we have 1/2 times negative 9.81 meters on top, and then seconds times seconds in the denominator. And then 1.5 squared times second squared is 2.25 seconds times seconds. All the seconds cancel. And all this is equal to pi. And so now do this multiplication, and you get that pi is equal to 30.66 meters. So the height of the bridge is 30.66 meters. Any questions about that? Yes. So I moved. So the pi is on the right side of the equation, and it's positive. This one's negative, but I added it to both sides to get it over to the left side of the equation. And so now we have a positive on both sides. And then in the last one, I just flipped them to the other sides. You can just always flip them. No, I see what, yes, thank you. I'm doing a lot of this stuff today. Thank you. That's important. So I flipped it over to the left side, or, added it to both sides, and that made this be positive. Sorry about that. So here they're both positive. You could have also done this problem by choosing your position equals 0 to be the bridge. And then you would have been trying to figure out how far it fell before time final. And so you would have been calculating P final. You would have gotten a P final of negative 30.66, which would have told you after 1.5 seconds, that object was 30.66 meters below the bridge, So there's flexibility in how you do it there. Any questions about that one? Let's do one more. Yes. Is that not what it came to? That's way, way off. Oh, because in my solution here, I use 2.5 seconds, not 1.5 seconds. Thank you. So what's the number you got? That's a much lower bridge. Okay, so here's another example. So let's say that a ball is thrown straight downward from the top of a 10-meter wall. And let's say that it takes 0.7 seconds to hit the ground. What was the velocity of the ball at the instant it was released? So it looks something like this. So here's your 10-meter wall. Here's the ground. Here's a person on top, throwing it down to the ground. Okay. Yeah, that looks comfortable, yeah. So the difference here, what's the difference between this and the last problem? I mean, the numbers are different, but the difference is in the last problem, it said the ball was dropped. And so we know that the velocity was 0 when it was released. In this one, it's projected, launched downward. And so we know that there's some negative velocity at the start. And we want to figure out what that is. Okay. So first, we have to choose these 4 things. Time equals 0, time final, p equals 0, and the positive direction. Time equals 0 is when it's released. Time final is when it hits the ground. Position equals 0 is the ground. And the positive direction is up. Okay, and now we'll go through the variables. Do we know time final? Yep, that's given, 0.7. Do we know position initial? Yeah, that's positive 10 meters because 0 is at the ground, positive is up, and the ball is released from 10 meters up. So PI is positive 10 meters. Do we know position final? 0, yep. Do we know velocity initial? That's what we want. And do we know velocity final? No. So, oh, and we know acceleration, free fall. Is there an equation that works with these? The second one, yep. So position final is equal to position initial plus V initial times time final plus 1/2 times A times TF squared. So 0 is equal to 10 plus 0.7 seconds times VI plus 1/2 times negative 9.81 meters per second squared times 0.7 seconds squared. So the first thing, I didn't use the units on that first term. That should be in meters. So the first thing we can do is combine the things that have the same units and we don't have any variables included. So 0 is equal to 10 plus whatever this is. You have to square the 0.7, square the seconds, multiply the half, multiply the negative 9.81. So that comes out to be 10 meters minus 2.4 meters, and then that middle term plus 0.7 seconds times VI. So 0 is equal to 7.60 meters plus 0.7 seconds times VI. So negative 0.7 seconds times VI is equal to 7.60 meters. And then VI is equal to 7.60 meters divided by negative 0.7 seconds. And you get that the initial velocity is negative 10.86 meters per second. Does it make sense that that velocity would be negative? Yes, because it's being thrown down and our positive direction is up. That's like 25 miles an hour or something like that. It's not a very good throw, not a very hard throw, but it's a pretty good hard throw for somebody hanging on a wall by their chest like that. Yes. Any questions about that? If we calculated now the final velocity, would it be more negative or less negative or positive? So now if we calculated the velocity at the instant right before it hit the ground, is it going to be speeding up in the negative direction? Or is it going to be slowing down in the negative direction? Or is it going to be positive? Yeah, it's going to be speeding up in the negative direction. So it'll be like negative 14 or something like that. Because if something has a downward velocity and its acceleration is also down, it has to be speeding up. This is the last of the stuff that's going to be on the test next Tuesday. So you want to get as comfortable as you can with all of the 1D kinematics problems before then, okay? Yes, I'll give you all the equations, yeah. Any other questions? Okay, see you Thursday.